to the end. So I've kind of put together pieces from a couple of different papers, but the heroes of the story here are Mattia Miotto and Alex Martirosian, who were at different times PhD students with me. And this is basically a summary of what I said, but the whole thing condensates here that RNA crosstalk is appears to be highly non-specific and long range, okay? But I want to try and give something that I don't usually do, because I don't usually have these kind of messages, but something that is more, let's say, food for thought, I believe. So, I want to be clear about one thing, okay? I don't think that inducing crosstalk is the job of microRNAs. MicroRNAs are there to silence genes. That's what they do, okay? And they're very good at that, right? However, it just so happens that there's also crosstalk, right? There's some significant level of crosstalk. And crosstalk is something that can help expression levels to coordinate across large distances over the transcriptome. And there's not a lot of mechanisms that can do that, okay? Because usually interactions are highly specific, and this is a non-specific one. So it's not very strong, but it's there. There's lots of these interactions weak, you know, and they really help in coordinating expression levels when needed. There's some evidence that microRNA do actually play this role in cells. Now, the interesting thing, I believe, of course, carrying biological information over large distances is something that cells do all the time, okay? You imagine a photoreception. When, a photon touches your retina, the information that the photon has arrived is, you know, cascades across a multitude of processes until, you know, your neuron reacts, okay? So that's a carefully tuned biochemical cascades of event, phosphorylations, that basically amplifies the arrival of a single photon without amplifying the noise associated to it, which I find mind-blowing. I don't know about you, every time I read about photoreception, I'm blown away. But the point is that biological information needs to be carried across large distances, and cells usually invest a lot of resources into making sure that it happens, okay? It happens precisely, without amplifying the noise. While RNAs appear to have a sort of soft way of doing this, because all of these small non-coding RNA molecules, like microRNAs are one of them, that you find in cells, they can actually achieve that without extra expenditure compared to apparently without extra expenditure. And this seems to be somewhat encoded in the networks, because it really depends a lot on the degrees of the interaction, so on the structure of the network. So there seems to be something, so I don't want to make too big of a statement, but you know, they seem to have evolved together with the function of crosstalking. So I find this extremely interesting, and I just hope that I've interested you in weak interactions among biological molecules. So that's basically it. Thank you very much.
There is any question?
Yep.
No, I mean, if other has a question. So the question is the following. So you say if you rewire the network, you basically observe the same rough distribution.
If I rewire while keeping node degrees.
Node degrees.
Yes.
The question is, what if you do the same thing, selecting only on septamer, heptamer, and 9?
Ah, we did that. Yes, we did that, selecting only on each interaction class. I think, well, basically...
No, because I mean, what I think is that maybe if you include everything, it's true that is random.
No, it's...
it's still random in...
Yes, actually this is a... So, because we do everything on a computer, right? We can also look at which specific property of this crosstalk network is controlled by what class of interaction. So if we can remove by hand certain interactions and do the whole calculation again and see what changes compared to... So we know what aspect of the crosstalk network is controlled by the weakest interactions, for example. So we also try to do the randomization thing. Now, I actually don't remember... I mean, the general picture is that as long as you keep node degrees, the results are robust, okay? But maybe we look at the paper together and look at the figure.
One question.
Yes.
So thank you. Very, very interesting. It still somehow turns in my head that not having into account the transcriptional network that is, before the existence of microRNA, the only thing that we thought about was transcriptional networks. But in the transcriptional networks, you have interesting feedback loops that compensate for these strong, susceptibility cases, right? So in a way, what this is telling us is the background in which the transcriptional networks have to be added to,
Yes,
right? Because these feedback loops will be essential to some processes.
Yes, I agree. Yes. I mean, the only thing that I'm not sure about, because I don't really know, is how much how well transcription factor levels correlate with transcript levels. That's something that I never really understood.
No,
but if
they don't need to. Oftentimes they do. Oftentimes transcription factors are post-transcriptionally regulated. So
okay. No,
but there is something that you can always say that there is. You can assess the amount of activity of the transcription factor based on how many of its targets have been changing depending on the conditions, right? But that is, I think that what you are, this is kind of the background in which these transcriptional networks will be operating, and it's an important one, right?
Yes. No, also probably the thing you mentioned in the beginning about limiting factors here that we're neglecting, that will also,
Well,
Done?
done.
Done.
Let's thank Andrea again.